trial of a new drug suggests it does its work. Unfortunately, there are tons of problems with the application of p-values. First, and most obviously, the cutoff of 0.05 is completely arbitrary. If an intervention is studied and found to provide outcome benefit with a p-value of 0.045, it's not dramatically more believable than if the observed benefit had a p-value of 0.055. Another problem with p-values is that researchers are so focused on them, largely because they know their potential future readers feel most comfortable with them, that they neglect other statistical tests which may actually be more appropriate for their particular question or type of data. However, the most fundamental problem with how clinical medicine uses p-values is that it produces a continuous distribution of probabilities, so a positive versus negative dichotomy. clinicians are familiar with this relationship. The odds of disease being present after a test has been performed is equal to the odds of its presence before the test, multiplied by the likelihood ratio from the test. In other words, a so-called positive test result doesn't necessarily mean that the person has the corresponding disease, because it also depends on how probable the patient was to have the disease to begin with. An analogous relationship exists for interpreting studies. The probability that a statistically significant result demonstrates a true effect is dependent upon not just the statistical strength of the findings, but also upon the probability that the effect was true prior to the study. Or in the words of Carl Sagan, extraordinary claims require extraordinary evidence. If we reduce trials to just being positive or negative on the basis of p-values, we lose our ability to apply this reasoning. All this goes back to the probabilistic nature of clinical research. Sometimes when there is no true effect of an intervention, the data will look like there is. And when there is a true effect, sometimes the data will look like there's not. It doesn't necessarily mean that the investigators made a mistake, but it can still lead them and us to the wrong conclusion. And no matter how well designed a study is, statistically predictable error cannot be fully eliminated. The fourth and final contributor to false research findings is conflicts of interest. We like to think that science is always objective, and that scientists' one and only goal is the pursuit of truth, free from other influences. But unfortunately, that is not reality. Many factors get in the way of that pursuit of objective truth. Some factors are conscious and some are not. Some factors are innocent and some are not. Scientists and clinical researchers are under a lot of pressure. They feel internal pressure from an inherent desire to make discoveries and grow their reputation, and they feel external pressure from their institutions to publish papers and bring positive publicity and national recognition that will be used as justification for their academic promotions. They also feel external pressure to publish because their success at being awarded grant money to continue the research is largely dependent upon prior success at getting papers out to the world. There's a saying in academia, publish or perish. Research productivity is seen as synonymous with the number of papers published. Unfortunately, because this leads to terrible incentives. Positive trials are more likely to be published than negative ones, and replication are rarely published. And the more eye-catching or unexpected the conclusion, the more likely the study will be published. And therefore, the consequences of how these conflicts of interest and these features of publication bias interact